Okay, so here's we reviewed the definition of one-to-one and onto, and we worked on proving these two theorems. If f is a function from A to B, and g is a function from B to C, and f and g are onto, then g composed with f is onto. I think it's working still. It worked last week. We got it this morning. So, and then half the class worked on this theorem. If f and g are one-to-one, then g composed with f is also one-to-one. Okay. So now we're going to look at the proof of the first statement. If f and g are onto, then g composed with f is onto. Try to turn the camera. I gotta look at the camera and then turn the camera. All right. Let's see if we can do this. All right. See if I can zoom in on TV. Is that as far as it zooms in? All right. Well, I posted these proofs online. All right, so I'm going to go over this. Can you guys read these proofs? Okay. All right. So suppose same function, same theorem. Suppose f and g are onto, then g composed with f onto. All right. So we need to show that for any little element c of the codomain of this function, there is an element a of the domain such that g composed with f of a equals c. That's what it means for g composed with f to be onto. Okay, does that make sense? So we're going to you start with an element little c in set C. Okay, and then I've got to find this a, so that g composed with f of a equals this c. Okay, like I said, I'm going to give you a handout with all these on here, so if you want to write down your notes, that's fine. But so all right, so since g is onto, I'm guaranteed that there's an element of b in G's code, in G's domain, that maps onto that little c. Okay? So since G is onto, there's a little element b in the set B such that G of B equals C. Let me pause. Does that make sense? I chose an element C of C. Since G mapped B onto C, I'm guaranteed that there's a little b with G of B equals C. All right. So now this B is in this set as well. So now I can find a little a that maps onto that little b because f is onto. Okay? So since f is onto, there is an element a in the set A such that f of a equals b. Now put those together. So g composed with f of a, well so g composed with f of a is the same as g of f of a. But f of a, we said equals b, so that equals g of b. But g of b, we said equals c. So what I can conclude is that g composed with f of that little a will equal c. Therefore, I've produced the a that I need, and I can conclude that g composed with f is onto. Okay? Any questions? We start with a little c, and then because g was onto, I can find a little b. And because little b is in B and f is onto, I can find a little a. And then you compose those two, and you get g composed with f of a equals c. Okay? Therefore, g equals with f. Any questions with that? All right, so the next theorem was about one-to-one. So basically, just in the statement of this theorem, just change the word onto to one-to-one. Okay? All right, so let me look at the proof of that theorem. Okay, so here's the theorem. It says, suppose f is a function from A to B and g is a function from B to C. If f and g are one-to-one, then g composed with f is one-to-one. All right. So what does it mean to prove that g composed with f is one-to-one? You start by assuming that g composed with f of x equals g composed with f of y. And you have to show that that forces x to equal y. Okay? So you start with this assumption, and you have to conclude that x equals y. Okay? And you'll see we'll just kind of unwrap the composition and use the fact that the g and f are both one-to-one. Okay, here's the proof. All right, Right. So you assume whatever function you're trying to show is one-to-one. You start assuming that that function, the two values of the function are equal. So g equals f of x equals g equals f of y for some x and y in the domain.
What is that? So you're not assuming that f and g are wrong, or that is what you're doing?
I am. I'm going to use that down here in this part of the proof.
So what are you assuming?
I'm assuming that g composed with f of x equals g composed with f of y. And I have to conclude that x equals y. And then I'll be done.
They show the words backwards.
I feel so you're assuming kind of like the end of the application?
No. Look at the definition of one-to-one. If f of x equals f of y, then x equals y. That's what this means. F of x equals y implies x equals y. So how do you prove a if-then statement? How do you prove an if-then statement? You assume this and show that. So change it to g composed with f. Right? So to show that g composed with f is one-to-one, I will assume that g composed with f of x equals g composed with f of y, and conclude I'll be done when I've shown that x equals y. Okay? Back to the proof. So I assume that g composed with f of x equals g composed with f of y. The definition of composition means that this statement is the same as saying that g of f of x equals g of f of y. That's just the definition of composition. Okay? Now it's kind of, you can just peel off the layers of the functions, because if g of something equals g of something else, since g is one-to-one, I can conclude that the inputs are the same. Well, in this case, the inputs are f of x and f of y. So that's where I'm using the fact that g is one-to-one. If g of something equals g of something, then those two inputs have to be the same. All right, now you have this statement, f of x equals f of y. But since f is one-to-one, I can conclude that these inputs must be the same. So I can conclude that x equals y. But that's what I needed to show that g composed with f is one-to-one. I assume that g of f of x equals g of f of y, and I'm done when I've shown that x equals y. Okay, questions? So you might have more insight, on the one that you practiced working on for the last 15 minutes or so, but any questions about that? So that's the way the proof goes. So kind of start with the you got to really go back to definitions. It's really you're using an if-then statement for your definition. So you assume this and prove the conclusion for both of these. Okay. So you said if p is in little b, then there exists an A and A. So you start with assuming there's an element of the codomain, show there's an element of the domain that gets mapped onto it. Okay. Any questions about that? Let's look at the statement of these other two theorems.